Hi, folks. Yeah, we're running out of time, so I'm gonna record this video so that you will know how to use the beam column selection table or design table, whatever you wanna call it. Uh, so yeah, so basically this table is nothing fancy. In fact, if you know how to use the beam table, and if you know how to also use the column table, um, you're already done. I mean, this table does not really provide anything new. It's just a convenient place to find all the numbers. So I'm gonna explain that with a very simple problem. Let's take a look. So, okay, well, let's not get carried away too much. Um, so I'm gonna use a very basic example, which is say if we have a beam column that is this size, and it's actually getting compressed by 800 kips from above, and laterally at the middle point of this 30 feet height column, it was loaded in strong axis bending with 200 kips. In the weak axis bending, so you're bending about weak axis, it's 50 kips. It's wind, seismic, I don't know, whatever, okay? The question is that is it adequate? So the point here is that beam column design is actually pure trial and error. If you still recall when we do beam design, there's a beam design chart. It will actually, you can follow a set of rules that will give you the lightest cross section. But yeah, unfortunately, not for beam columns because there's just a lot of things going on. So you have to do trial and error. The table will actually help you to do that a little bit earlier, a little bit easier, so that you don't have to, manually calculate all the capacities. Once you know how to do a design check, like what I'm gonna show you, design is just try different cross section until you get the right one that is not too heavy. In this example, we want to keep everything at the simplest. So we're gonna assume all the loads are already factored. So you don't need to worry about load combination. Those are already combined for you. And then in here, we're not considering second order amplification. The B1 and B2 factor we talked about in class. In this case, although it's like a pen, it is a braced condition. In real design, you do need to consider B1 amplification, which you can follow the formula to do it. But yeah, this example just talk about how to do the table, so we're not gonna go there. So the question is adequate. Really, you need to just go all the way back to chapter H. What it says is that you need to look at the interaction formulas depending on the added axial load to your axial load capacity. If it is more than 20%, then you do this. If it's less than 20%, you do this. Okay, if you look at those interaction formulas, basically whatever's on the top, like PU, MUX, MUY, different textbooks, different code, they might have different names, but whatever's on the top is what is caused by the external load. Okay, and they are the real maximum moments, maximum force. In real design, they need to be amplified, or they need to be calculated from a finite element software that enables second order analysis. So those you do that, get those top numbers by structural analysis. So in this case, it's actually quite simple. I mean, the P, I use PR, it means required, is simply just 800K. I mean, that's it. I mean, there's, That's it. The moments, here you can see if I'm getting a concentrated load at the mid-span. Everybody knows the moment diagram going to be a triangle. The top one would be PL over 4, so that's the maximum moment. Again, if it's real design, you need to amplify those, but in this case, we're just, hey, we're not going to do that. Okay, we're going to ignore that. Okay, now you got the top part of the equation figured out. You need to find the bottom. The bottom is actually 3 different designs. This one is the column design. You need to go to the column table. This one is a beam design in the strong axis, where you need to go to the table, 3/10, which is a chart. You need to do that. And then this one is bending about the wake axis, which is much simpler. You can just calculate it, but because there's no lateral torsional buckling. But anyway, you need to calculate it if you don't have a table. But now we have the table, so we're going to take a look at what we can do with the table. So the table, of course, like every other table, you need to say, okay, find your cross-section, right? And then take a note to those 2 numbers, Fy and Fu. If your Fy and Fu are not those 2 numbers, you can use the table. I mean, because in the table are generated by those code formulas, and the formulas, a lot of things are related to those 2 numbers. So make sure you check that. Okay, so conveniently, we are already there. Okay, well, so W40 by 397. So this table basically have a kind of shared span, which is, if you read it, it is both the effective length LC for the column. I mean, you recognize this. This is the wake axis column L. We call it LY. They call it LC, whatever. And then it is embrace length LB. Okay. So you have the available compressive strength, which is the column table on this side, left side, and you have the available strength, which is the beam bending strength on this side. So you're like, okay, well, great. So what is this? You think about it. This one, strong axis bending, the embrace length is 30 feet. And then the K is a pen, so K is 1. So this is really simple. Strong axis KLX is 30 feet. If you look at the wake axis, which is the LY, same situation, okay, 30 feet. In cases they are different, you need to find the equivalent KLY from the X, and then go with the longer one, because that will control the design. But in this case they're the same, so we just go with this. So 30 feet, you look in here, 30 feet is right here. So you just read it, okay. 2580, because we're doing RFD. 2580 kips. 2580 kips. Okay, now here we need to get the MYX, which is the bending in the strong axis, which we will have lateral torsional buckling. So you go with unbraced length, like this one. I didn't say this one's braced here or anywhere, so you just assume it's braced at the support. So unbraced length is actually 30 feet as well. So you go here, come here, 5400. Okay, 5400. But here is the thing. This is not necessarily right, because the table, apparently just like all the other tables in this one, does not consider the shape of your moment diagram, which means all the values within this table are assuming CB equals to 1. Um, but you're like, okay, well, my CB is not 1, right? I have a triangular moment diagram, and we know, I mean, if you don't know, you can calculate it yourself, but if you have a triangular one, the CB is actually 1.32. Okay. So you do the calculation, and then you find out, let me actually do the calculation, right? So 5400 times 1.32 equals to 7128. Okay. All right. So is that correct? Yeah, it's not correct. Why? I mean, a lot of you probably already noticed. Because this number cannot be exceeding the plastic moment. Then you're like, oh, where am I going to find the plastic moment for this guy? Yeah, of course, I can go to part 1 and then, find Z and times the Fy, which is this one, and then times 0.9, then that's my, plastic moment. But in this table, you can actually find it. Remember, when you are fully braced, which means your LB equals to 0 or very small, you actually will reach your yielding plastic moment. So if you actually look at those numbers, go up, then up to a point, then it won't change anymore. So that's actually corresponding to the flat line in our system, and then that's actually the plastic moment. Another way to look at it is you look at the LP here, right? LP here for this cross section. The LP here is 12.9, so which means anything below 12, including 12, they reach plastic moment. So the plastic moment for this cross section is actually 6750. So I'll say, okay, well, this one is actually smaller than MP, which is 6750. So use 6750. All right. So finally, what is this guy? Oh, this guy is the capacity when you bend it about the wake axis. Where is it on the table? It's actually down here. Available strength in flexural about YY axis. You're saying, oh yeah, it has nothing to do with LB. Yeah, because there's no lateral torsional buckling. It's just yielding. Sometimes there's local buckling of the flange, and then if it's in the table, it's already accounted for, so you don't need to worry about that. The cross section here, W40 by 397, going all the way down, 1130, right here. Okay. And because there's no lateral torsional buckling, there's no CB or whatever to talk about. So we got this guy. Oh, let me. How do I get my bar back? Anyway, here we go. We got this guy. We got this guy. Come on. Let's just paint it. And we got this guy. Oh no. Got this guy, and we got this guy. So now it's time to just use the, let me change it to different color. So everything I marked in, oh, yeah, sorry, I think I made a mistake. Everything I marked in blue is the upper part of the interaction equation. Those two. Everything I'm marking red is what I discover from this table, which is the bottom part. So the first thing is to compare those two. So those two, if you just do 800 divided by 2580, that'll give you 0.31. If it's 0.31, it is greater than 0.2. So we need to use this guy, okay? Well, we can just do it. Let's do it, okay. Plus, well, it's a not, right? 8 divided by 9, and then times a parenthesis of this one over this one. 1500 divided by 6750 plus then this guy 375 divided by this guy 1130, and then I'll close the parenthesis, and yeah, that's it, right? That should be it. Okay, equals to. So the entire thing, this interaction formula equals to about 0.8. So if it's about 0.8, if I didn't make any mistake, you can check, but anyway, it's smaller than 0. Oh, not smaller than 0, smaller than 1. So interaction value equals to about 0.8. It's smaller than 1, so we are okay. Which means, to answer back this question, is it adequate? I'll just say yes. Okay, so yeah, this is an example where I showed you how to do this calculation and how to quickly, if you find a cross section in the table, be able to pull all the numbers to do all those calculations. All right, thanks. I'll post something later.